and these are going to be called the principal stresses. And if I write now this stress tensor in this new coordinate system, it's just going to be S11 prime, S22 prime, and S33 prime, where these numbers are not going to be the same as the numbers I have over here. They're going to be different. And whenever we do that, we like to simplify this a little bit further, and we write this stress tensor just as S1, S2, and S3. Remember, all shear stresses are going to be 0. That's the definition of the principal direction. So and we call these numbers principal stresses, and we like to order it saying that S1 is going to be equal or greater than S2, and S2 is going to be equal or greater than S3. There's going to be always a coordinate system that allows me to do that. How do you do that in with numbers? Well, there are two solutions. Probably you remember the Mohr circle. Do you guys remember the Mohr circle? If you don't worry, because we're going to talk about the Mohr circle in a few classes. So you can use the Mohr circle to calculate these numbers out of these, or as I told you before, you can use eigenvalues. And for example, in MATLAB, I think the command for eigenvalues is EIG. EIG of the matrix will give you the eigenvalues and eigenvectors. Yes, sir, you have a question?
Yeah, is S1 is representative of SH min, correct?
No, in this case, this is general. It could be anything. It could be SV, could be SH max, could be SH min. It will actually depend on the location in the earth in which you are and what is the stress regime at that particular location. So it can be anything. You see, these are the same, S1, S2, S3. And it could be SV, could be SH max, could be, well, it won't be SH min, but it could be SV or SH max. Okay, so I hope that by now, more or less, you have an idea about what these principal stresses are. But let me show you one example that probably is going to illustrate this a little bit better. And that's why I brought this cube over here. So you can see the cube, right? It's a cube. Now when you see in the camera, it doesn't look that much like a cube, but it is a cube. If you don't look at the cube perpendicular to the faces, you will see all kind of colors, right? For example, there is a dark green over here, there is a light blue over here, pink, red, violet, it looks like orange, and it's a mix of colors. That's because you're not looking perpendicular to the face, right? But if you were to find the direction, which are the direction in our case of principal stresses, and if you look just in that particular direction, you will see just one value. So for example, this would be the principal value in the direction perpendicular to this face. This one is just yellow, and this one is just blue. You see, there's just three. When you happen to look in the right direction, it's just one number. If you don't, you will see as a combination of colors. And it's the same thing as what we have over here. If you find the principal directions, it's just going to be one number, and it's going to be normal stress. If you don't, you will see normal stresses, but you will also see shear stresses. most of our problems are going to deal with normal stresses, but shear stresses are also very important. For example, shear stresses are likely responsible for microseismicity. Are you guys familiar with microseismicity? It's a tool that is used in hydraulic fracturing for measuring how far the stimulated reservoir volume goes, to see how far the effect of the hydraulic fracture went into a particular operation. So, and it's also responsible for rock failure. We're not going to see too many problems of calculating eigenvalues or calculating principal directions, but the concept is very important because we're going to be talking about this all the time. Yes?
So when we have shear stresses alongside the normal stresses, are the diagonals still the principal stresses, or we can't say for sure?
Say again, when?
If you have shear stresses alongside the normal stresses, do
Yeah.
we know for sure which ones are the principal stresses?
We don't know. If we have shear stresses on a face, this one for sure is not the principal direction. And the same with all the others. If, for example, you got shear stresses S1, 2, and S2, 1, but these two are 0, well, I know this one is a principal stress. And for example, with vertical stress, it happens that most time vertical stress is a principal stress. There are no shear stress in this or that direction, but we generally do not know what the orientation of horizontal stresses are. Usually it's not going to be aligned with the east or the north or whatever direction we use for our coordinate system. Okay, let me see if I'm forgetting anything over here. Okay, very important. We know about total stresses, we know about pore pressure, and we know about effective stress. So how do I compute now effective stress using these matrices? Well, first of all, I'm going to need pressure. What is going to be pressure if I want to write it in 3 dimensions? Or if I want to make an operation? Well, let me start with saying that effective stress now as a matrix is going to be the total stress as a matrix minus the pore pressure. But I have a problem here because pore pressure is just one number. So what would you do in order to make this compatible? Because I cannot add up scalars to a matrix or a vector to a matrix. What would you do in this case?
Multiply by the identity.
Very well. You multiply by the identity matrix. So now sigma, effective stress, sigma 1,1, sigma 1,2, sigma 1,3, sigma 2,2, sigma 2,3, sigma 3,3. Remember that sigma 2,1 is going to be the same as that number, and the same with the others, so I'm not going to write them because I know those are the same. Is going to be equal to S11 S wait, this wrong. S12, S13, S22, S23, and S33 minus, now I'm going to make this multiplication already here. It's going to be BP, BP, and pore pressure again. So if I want to put everything together, it's going to be S11 minus pore pressure, 0, wait. S12, S13, S22 minus PP, S23 and S33 minus 3p. And notice that this makes a lot of sense. For pressure, let's say that I throw this into the Town Lake. As it goes down through the water, do you think this solid is going to distort in shape, like when you have shear stresses? For example, in this case, we come back to this one. When you apply a shear stress, you will tend to pull in this direction and kind of like compress in this direction. Can you see that? And as a result of that, the shear stresses are going to change the angle between the faces and are going to cause what is known as a shear distortion. Something like this. So my question is, if I throw this cube into water, do you think it's going to distort like this? Not very likely, right? Because the pressure is the same in all directions. If it goes very deep, maybe it's going to contract in all directions, but it's not going to distort like that. Pore pressure cannot apply shear stresses. And because pore pressure cannot apply shear stresses, then these terms, sigma 12 is going to be equal to S12. The shear stress, the total shear stress is going to be equal to the effective shear stress. Pore pressure is just going to affect the normal stresses, because pore pressure does push in normal direction. And because of that, then we're just going to have the normal stresses affected by pore pressure when we want to compute effective stresses. All right, I think we are getting close to what I wanted to say for today. Any question about this? Yes?
So the sigma represents total stress, or is it the effective stress? Just to be clear. On the left-hand side, like the left-hand side matrix.
So this one is total stress.
Okay.
This one is effective stress. And this one is pore pressure. And this one up here is effective stress too. So just for the sake of completeness, let me write everything here. How's the homework going, guys? Any questions? Can I help you with that now?
Oh, the last question.
Yes.
There's I don't know, for me, like the file, so the file has a lot of bad data in it, and it doesn't seem like they're lined up correctly. I don't know if that's just something I need to figure out, or.
I'm going to check the file. In my computer, it shows up correctly, but last time I went to GitHub, I noticed that it wasn't like that. So let me check that quickly. Okay, this file is fine, okay? This is a tab, the limited file, you should be able to open it. So you can go here, you do copy and paste, and you have it, okay? For the other one, it should be also tab separated, okay? I'm gonna check it again. But it should be the same as the other one. It just has like 20 columns, so it doesn't fit in there. All right, guys, I'll see you on Wednesday.
Professor?
Yes.